Although it turns out that the Earth can be approximated as a sphere, a better approximation of the Earth is an ellipsoid. An ellipsoid is an ellipse that's then rotated around one of its axes. In this case, the axis between the North Pole and the South Pole. An ellipse has a semi-minor axis, which would be the shorter axis, which is shown as B here, and it also has a semi-major axis, which is the longer axis, that's shown as A here. And in this case, it would be spun around B in order to create the ellipsoid. The reason that the Earth is better approximated as an ellipsoid is because as the Earth spins on its axis, the centripetal force makes it bulge out in the center, so that it actually has a longer axis near the equator than it does from the North Pole or to the South Pole. So all we need to do then is find an ellipse that approximates a fit to the surface of the Earth. And this has been done several times over the history of the Earth in order to try to best estimate based on the amount of points that we have. So in this example here, you can see that maybe if we just have point 1 and point 2, ellipsoid A would be a fine representation because it goes directly through point 1 and point 2. However, as we start collecting more points, point 3, point 4, point 5, point 7, point 6, we see that no longer, the solid line here no longer represents a best fit to all of that data that we have. Now we draw another ellipsoid, ellipsoid B, which doesn't necessarily go through any or all of those points, but is the best estimate for getting as close as possible to all of those points that we now know represent the surface of the Earth. So we can have different ellipsoids. Each of these ellipsoids is going to have a certain size, and they're going to have a center. That's called the origin of the ellipsoid. For the first North American datum developed in 1927, the ellipsoid of the Earth was not pinned to what we think is the center of the Earth. It was pinned to a specific location on the surface of the Earth in Kansas for the North American datum. As we've been collecting more and more information with satellites, now we're coming up with we come up with a better ellipsoid whose center represents approximately the center of mass of the Earth. So it's no longer pinned to any place on the Earth. It's pinned to this center of mass of the Earth, and that would be an approximation of the used in the NAD 83, or North American data of 1983. One thing to remember is as we talk about things like geographic coordinates and all, what we're really going to be talking about is some location on the ellipsoid. And then in order to get to the actual location on the surface of the Earth, we may have to go up or down in order to reach that location in a perpendicular fashion. So there's the ellipsoid, we draw a line perpendicular to it, and at some point that intersects the surface of the Earth. So the ellipsoid does not account for all of the little bumps and mountains and hills on the surface of the Earth. It just gives our geographic location. Ellipsoids are good if we're measuring things from space, such as with GPS coordinates, but a lot of measurements taken in the past were actually done based on the geoid. So the geoid represents a surface where all of the pull of gravity is the same, and sometimes we call that an equipotential surface. We can see here that in some places it shares locations with the edges of continents, such as the eastern coast of Africa here, but in other places we have variations in the geoid that are big. One way to think of this is where sea level would be if we were able to cut canals through all of these continents. How high in those canals would the water rise? And that would be part of the geoid. The other part of the geoid is where the ocean is, and the surface of the ocean can actually go up and down based on density of rocks or other features that influence how strong the pull of gravity is at any potential location. The geoid was useful when they were mapping based on things like plane tables and compasses and other things that had some indication of what flat was, whether that was a plane table or a compass that had an inclinometer on it, so you could see how things were flat, and then things were measured from there because it was relying on the pull of gravity. So historically, a lot of mapping has been done from the geoid, And once again, this geoid is not going to be the same as the ground surface. It's just going to be a surface that represents where sea level would be if this ground surface was not here. And we can see in this case it can be above the ellipsoid, as we see here, or it can be below the ellipsoid. The geoid and the ellipsoid can cross each other. So here's a representation just to kind of show exactly that. We have two different ellipsoids here. They're both ellipsoids, but their major and minor axes are tilted. They have different centers associated with them, and they were created in different ways. The geoid can be above both of these ellipsoids. It can be below both of those ellipsoids, or it can be above one and below another. So all of these things are possible. I think the important thing here to remember is that geoids were popular to measure from when people were doing traditional type of surveying, like with compasses and plane tables and alidades and those sorts of things. And now that we're taking a lot more measurements with GPS and satellites, the ellipsoid has become much more important because we can get a lot of points and then come up with an ellipsoid that best approximates the surface of the Earth.